Okay, so today we're going to go over Unit 7B, combining probabilities. For many of you, this might be a little bit of a harder section. This is one of the harder topics I actually teach in my statistics course. Obviously, we're not going to go as in depth as you would if you took a full-on statistics course, but this is one of the topics that I have found students have a little more difficulty with. So be sure to, come to office hours or whatever, and or meeting times and ask for help. Um, so let's get started. So there's two big things we're going to talk about in this section, end probability and or probability. Well, actually, I'm sorry, end probability with independent and dependent events. So two events are independent if the outcome of one event does not affect the probability of the other event. So it's really important that you guys understand that it does not affect, okay? So that means like when you flip a quarter, if you flip a quarter in the air, um, when you flip a quarter in the air, you do not, you have a 50-50 chance of getting heads, one out of two getting heads or one out of two getting tails. Now, if you flip the quarter again, does it really matter what you flipped the first time based on, or to give you the new outcome on the next flip? So if I flip a quarter heads, I have a one out of two chance of getting heads or a 50% chance of getting heads. When I flip a quarter again, I still have a 50% chance of getting heads. However, what's the probability of doing that twice in a row or three times in a row or four times in a row? That's when we start getting where there's a little bit of difficulty for students to decide which is which. Okay, so independent events one event does not affect the outcome of the other. If two independent events A and B have individual probabilities, and remember this is how we write probability of A and the probability of B, the probability that A and B occur together is probability of A and B. So you'll also see it written sometimes like this, you guys, A, and then you'll even see this symbol sometimes. And it says the probability of A and B is equal to the probability of A times the probability of B. So that means in the quarter problem I was talking about, what's the probability of heads and then getting heads again, flipping a coin and getting heads again? Well, that would be the probability of getting heads times the probability of getting heads. But what is the probability of getting heads? Well, it's one out of two, right? And then one out of two. Okay, so that would be one out of four. Or you guys could have also done it this way. Alternatively, you could have done um, with decimals 0.5 times 0.5, which is 0.25. Both are correct, depending on what the question asks for. If it asks for fractions, you give 1/4. If it asks for decimal, you give 0.25. Okay. This principle can be extended to any number of independent events. All right. So suppose we're going to roll 3 dice. So what is the probability of rolling 3 sixes in a row with a single die? So you pick up a dice, you roll it once, you pick up the die again, you roll it again, and then you pick up a die again and you roll it again. So that's what we're talking about. So the probability of rolling a 6 and 6 and 6. They picked a bad number, 666. That's unfortunate. Okay, so we're going to do the probability of rolling a 6 times the probability of rolling a 6 times the probability of rolling a 6. Now, here's the thing. Are we sure we're able to treat this as an independent event? So what we're going to do is we're going to think about this. If I roll a 6 on my first roll and I pick up the dice and roll it again, is the dice now changed in any way, or is the probability of rolling a 6 again changed at all? And the answer is no. You roll from one dice to the next, you have a 1 in 6 chance of rolling a 6. On the next roll, you have a 1 in 6 chance. So that's what I'm going to do. I'm going to do 1 out of 6, 1 out of 6, 1 out of 6. And I'm assuming this is 1 out of what, 200 and what would that be? 36 times 6, 216. Let me just double check that on my calculator real quick. Yeah, that'd be 1 out of 216. Now, if they ask for the decimal would be approximately 0.0046. Let's do 4 decimal places. Okay, so once again, depending on how the question is worded, if they want the decimal, you give them that. And if they say round to the nearest, percent, this would be actually 0% if you rounded, or you might even say 0.4 of 1%. So it's not even 1%. It's almost half of 1%, or I guess you could even say 0.5 if you round it off. Okay, but it really depends on the way they word it and how it's asked. Okay, So now notice this is different than if you rolled 2 dice at once, right? The 2 dice at once was one from the previous section where we would say, what's the probability of rolling a 6? And then we would say, well, that could be 3 plus 3. That could be 5 plus 1 or 1 plus 5. That could be 2 plus 4 or 4 plus 2. Notice this is different, okay? So this is a different style. This is saying you roll one after the other, okay? So this is an AND probability. So now AND probability, and the other thing I want to remind you of is when you're doing AND probability, think multiplication. Okay, so N probability is all about multiplication. OR probability is all about adding and subtracting. Okay, so two events are dependent if the outcome of one affects the probability of the other event. The probability that dependent events A and B occur together is, okay, so what we're going to do is we're going to write down that formula real quick. So in your book, this is how they write it: probability of A and B. Now, this is for dependent events, meaning that the first event affects the outcome of the next event. You know, like probability of getting wet going outside if it's already raining or something like that, right? Or it's going to rain today. So there's a lot of events that are connected. So probability of A. And in general, whatever is written first, that's usually the one I write first, but it doesn't have to be that case. It's just the way I kind of was taught to do it. Times the probability of B given A. Now, what this means is that what's the probability that B occurs given that you know A has already happened? You're saying that A has already happened. So I like to write it like this. So you'll see me write it like this: probability of A times probability of B. And then I do this little line, given A has already occurred. So this line right here means given. Okay, so the probability of B given A has already occurred. So I'll write that a lot of times in the notes, or if you talk to me in class, where probability of B given A is the probability of event B occurring given that A has already happened. Okay, the occurrence of event A has already happened. So let's move on. So example of jury selection. A 3-person jury must be selected at random from a pool that has 6 men and 6 women. What is the probability of selecting an all-male jury? Okay. So let's write that out. Probability of all male jury. Okay. Now, what does that look like, you know, in terms of like notation? So what I'm going to do is probability of male and male and male, right? So that means we're going to select 3 people. Now, understand there are 12 people to select from, 6 men and 6 women. So this is actually going to be probability of male times probability of male times probability of male, if it were independent. So this is if it were independent. But here's the problem. Okay, now let's think about this. Okay, so let's suppose on the first selection you get a male, right? So on the first selection you get a male. So what's the probability of getting a male? That is 6 out of 12, right? But now on the next selection, now let's remember, on the next selection, how many people are actually left? Well, there's only 11 people left because you already chose somebody for the first selection. So now there's only 11 people left. And how many of them are male? Well, there's only 5 now because you chose them to be male, or the first person you chose was male. So now let's say on the second draw, we also got a male. What was the chance of that happening? Well, that would be 5 out of 11. Okay. So now let's on the third draw, how many males are left in the selection pool? Well, there's only 4 males left because we've already chosen 2. And there's only 10 people left in the entire pool. So this is how we can actually do this. Now, let me do some cleanup here. Let's see here. This is actually 1 and this is actually 2. This is actually 1 and this is actually 2. This is actually 1 and this is actually, I'm just doing cross canceling. And then this cancels and this cancels, 1 and 1. So we get 1 out of 11. That's what it looks like. Yep. Which is approximately 0.0909. For probabilities, I normally use 4 decimals. I'm not sure what your homework will ask for, but I usually use 4. Okay. Let me just make sure on my calculator, or let me do it over here, some little scratch work. 1/2, 5/11, 2 out of 5. Cancel, 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 cancel. Yeah, that would be right. I just wanted to make sure I did it right. Okay. So 12. Yep. Uh-oh. I think I might have 6 times 5 times 4. Let me double check you real quick, you guys. I think I might be missing a 0 somewhere. Divided by 12 times 11 times 10. No, the book is actually wrong. Okay. So we get this. Okay, so we're good. And this would be our rounded off answer. And again, if they want 3 decimals, then you would do 0.091, whatever the case may be. Okay. So just so we're clear, we could not use this because this was for independent events. And obviously, if you take somebody out of a pool and there's less people than there was beforehand, that changes the event. So this is what dependent events do. They change one event to the next, okay? Just like if you were drawing cards. So suppose I wanted to do a card problem. Okay, so suppose I was going to do a card problem and I said, find the probability of drawing 2 cards one after the other and getting the first card to be a king and the second card to be a, let's say, jack. No, you know what? Let's say face card. Hopefully this isn't too tough. Okay, so we're going to say probability of getting a king and a face card. Meaning the first card was a king, and then what's the probability of getting the second card given that the first card was a king? That's basically the way we have to think of it. So I'm going to write probability of king times probability of face card given that you already got a king, okay? Now remember, there's a jack, a queen, and a king. Those are the 3 face cards, and there's 4 of each of them, okay? So there's 12 total face cards, okay? How many kings? Well, there are 4 kings out of 52 cards in a deck, remember. In a standard deck. Okay, so there's 52 cards in a standard deck. So there's 4 kings. So what's the probability of getting a king on the first card? Well, that's 4 out of 52. Now we're going to multiply it by the probability of getting a face card, given that you already knew a king was drawn. So that technically means there's only 11 face cards now because we already drew a king. And then how many cards are left in the deck? 51. So let's do this on our calculator. So this is 11 over 663, or we could also do 0.0166 if we round it off, okay? So this is how we could do a card game. This is basically, you know, playing blackjack. This is the probability of getting a king and then a face card. So you're getting a 20 in the game of blackjack back to back. I just wanted to show you guys another one, okay? So now he says either/or probabilities. So not overlapping events. 2 events are non-overlapping if they cannot occur together. So sometimes they'll talk about it as disjoint or mutually exclusive, like the outcome of a coin toss is shown to the right. Okay, for non-overlapping events A and B, the probability that A or B occur is shown below. The principle can be extended to any number. So let me show you real quick. So here's the difference now. So when you're talking about or, think addition. Okay, so let's look up here real quick. So when we talked about probability of and statements, so of and statements, we thought multiplication, okay? When we come over here, and now we're talking about or statements, so this is for independent, non-overlapping events, we think addition, okay? Well, even if they're overlapping, we still think addition, but then we also have to throw in subtraction, okay? But for non-overlapping events, independent events as well, mutually exclusive, disjoint sets, we think of addition, okay? So let me show you how this works, okay? For non-overlapping events A and B, the probability that either A or B occurs is shown below. So probability of A or B is equal to the probability of A plus the probability of B. So this is the difference. This is no longer multiplying, this is adding or subtracting. So we're going to come over here and we're going to say, suppose you roll a single die, what is the probability of rolling either a 2 or a 3? So notice the big difference in and has multiple things occurring one after the other, right? With an or statement, it's basically saying you do this one thing and what's the probability of that happening? I mean, there's some gray area in there, but in general, that's the kind of the idea behind it. Okay, so suppose you roll a single dice. What is the probability of rolling a 2 or a 3? So probability of rolling a 2 or 3. So I'm just going to write out the formula, probability of 2 plus probability of 3. Well, we know that how many 2s are on a dice? 1, so 1 out of 6. Plus how many 3s? 1 out of 6. So this becomes 2 out of 6, which is 1/3. So the probability of this event occurring of rolling a 2 or a 3 is 1 out of 3. Okay, so not too bad, right? So what if I said probability of rolling a 2 or a odd number? Okay, well, how many 2s are there? 1 out of 6, right? Now, how many odd numbers are there? Well, there's 1, 3, and 5, so 3 out of 6. So this would be 4 out of 6, and this would be 2/3. Okay, so for when they're mutually or when they're not related events, it's actually pretty nice. It's pretty easy to work with. We're able to simply just add the probabilities and we don't stress out at all, okay? Now we have overlapping events, okay? Or events that there is, when you see this little picture right here, how they have this middle part shaded, that means that there are some face cards that are also clubs, or there is a queen that is also a club. That's when you have to worry about double counting, because technically you counted this queen right here, you counted that as part of this set, right? But then you also counted it as part of this set because it's a club. So it's just something we have to worry about. You counted it twice. Well, if I tell you to add something twice, how do I get rid of one of them? I subtract it off. So what we're going to do is we're going to write our formula for overlapping events A and B. The probability that either A or B occurs is shown below. So this is how we do it. Probability of A or B, and this is for when there is overlap. You say the probability of A plus the probability of B, just like before, but now you subtract off the extra second one that you counted, the probability of A and B. So you got to be careful with that. You got to know how many of them are in the actual and category, okay? So let's look at this problem. Let me see how much we have left. Oh, we're almost done, okay. So what is the probability that in a standard shuffle deck of cards, you will draw a 5 or a spade? So probability of 5 or a spade. Okay, so what we're going to do is we're going to say probability of a 5 plus the probability of a spade minus, now are there some 5s that are also spades? Yes, there is. So that means I counted it here and I counted it here. That same 5 can't be counted in both of them. So what I have to do is I say, okay, fine, I counted it twice. I'm going to subtract off one of them. Probability of a 5 and a spade. Now, if you go back and look, notice right here, this is an or statement, and the or statement actually uses an and statement in it to explain itself, okay? So now probability of a 5. Well, how many 5s are in a deck of cards? 4 out of 52, right? Plus, how many spades are in a deck of cards? 13 out of 52. Every suit, I don't need parentheses, I guess. every suit, remember, has a 13 cards in the suit. So 13 diamonds, 13 spades, 13 hearts, 13 clubs. Now, what we're going to do is we're going to subtract off how many spades are also fives. Well, there's only one of those, and there's 52 cards. Okay, so now this will become what, 16 out of 52. Divide by, what is that, 4? That would be 4 out of 13. Let me just make sure. 4 plus 13 minus 1 divided by 52. And we get 4 out of 13. And this is also approximately 0.3077 if we round off. Okay. So I actually like fractions better always, but in the homework or on the exam, they may ask for the decimal. So there you go. Okay. So this is pretty straightforward. Let's take it back to the other problem I had done earlier, where I said, find the probability of a face card or a king. So in the other problem, it was the probability, of a face card. Oh, I'm sorry, it was a probability of getting a king, and then on your next draw, getting a face card. Well, now this is an or statement, so its addition is not multiplication. So we're going to do probability of a face plus probability of a king. Now, are there some face cards that are also kings? Yes, there is. So we got to be careful. Minus probability of face and king. Okay. So probability getting a face card. There are 12 face cards, 4 queens, 4 jacks, and 4 kings. So 12 out of 52. Plus probability getting a king. There are 4 out of 52. Minus the probability of a face card and a king. So what face cards are also kings? There is 4 of them out of 52. So we end up with 12 out of 52 because these end up canceling. And this would be what, divided by 2? This would be 6 out of 26. Oh, I guess I should have divided by 4. Divide by 4, divide by 4. That would be 3 out of 13. And that should be 0.2308 if I round off. Okay. So this is the probability of getting a face card or a king. Okay. So again, if you think about it like this, if you were to draw this and you would have face cards here, and draw this and you would have kings here. You have this area right here in the middle that is face cards that are also, kings. And there's 4 of them. So this little space in the middle right here would be 4 out of 52. Okay, there are 4 face cards that are also kings. Very similar. I like their drawing up here that's from your book. Very similar. We would have like our 4 kings right here, right? Let me use a highlighter. We would have our 4 kings that are here, right? But then there's also this little section right here. That's the wrong color to use. There's this little section right here that would also have face cards that are also kings. So that's just something to think about. You really have to account for all of this while you're doing these problems. Okay, so the at least once rule. So suppose the probability of event A occurring in one trial is probability of A. If all the trials are independent, the probability that event A occurs at least once in n trials is shown below. So what we're going to do is we're going to try to basically, this is how the book shows it. I'll try to talk to you about it. So the probability of at least one event A in n trials. So let's look at an example problem. I think that's the best way to talk about this. It says, use the at least once rule to find the probability of at least one head when you toss 3 coins. So probability of at least one head on 3 tosses. That's kind of the nice thing is you see all of this. I mean, this is a lot to write, but I can just write it out. That's kind of the nice thing about probabilities is, again, they don't want you to write it like this. They would prefer you to write it like this: probability that X is greater than or equal to 1, where you would come over here and you would say X equals number of heads in 3 tosses. So that means that X could be 0 heads, it could be 1 head, it could be 2, or it could be 3. However, for our problem, we want at least 1 heads on 3 tosses. okay? So what they basically said with this rule up here is they say, well, forget about trying to find that because that's a little bit more advanced. Let me think. Yeah, so when you do stuff like that, you have to think for all the different possible outcomes. There could be, you know, heads, no heads, no heads. Or I guess you could say, well, there could be heads, tails, tails. There could be heads. I'm sorry. There could be tails, heads, tails. There could be tails, tails, heads. There could be, is that the only way? Okay, so those three things, we would have to find all those probabilities. I feel like there should be one more, but maybe that's it. Or it says at least one. So then it could also be heads, heads, tails, heads, oops, heads, tails, heads. It could be heads, 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 right? Those are all at least one heads. And you can keep going. I think there's a few more, but you guys understand you'd have to find each one of these. This would take forever. So what they're saying is when they say at least once, what you can do instead is you could say, well, what's the chance that that doesn't happen? So you find the probability of no heads and then do 1 minus that. Remember, everything has to add up to a total probability of 1. Okay. So if at least once means 1 heads, 2 heads, or 3 heads, well, what's the only situation where that doesn't have any heads? That would be no heads. So what we do is we do 1 minus that probability. Okay. So what I'm going to do is I'm going to say 1 minus the probability of no heads, no heads, no heads. Okay. So let's see what that looks like. 1 minus. Now, what's the probability of not getting heads? So use the at least once rule of no A in N trials. Okay. So what's the probability of that? All right. So think about that a second. So what we're going to do is, oops, let me turn the page real quick. So what we're going to do is we're going to say, well, wait a minute. Okay. What's the probability of not getting heads on the first toss? Right? Now, does the next toss of the coin affect or does the previous toss affect the next one? No. So it's 1 out of 2. And then what's the previous one? Well, it's 1 out of 2 again, right? So that's where they get this from. You see how it says not A to N number? That's a fancy way of saying, well, we know that you're just doing the same probability 3 times or 4 times or 5, whatever it is. So they do it to that power. So I could easily rewrite this as 1/2 cubed, which is 1 minus 1/8, which is 7/8. So the probability of at least 1 heads is the same as the probability of 1 minus no heads, which is 7/8. Okay, so that's how you can do those type of problems. Again, they're a little more difficult because you have to think, wait a minute, technically I should have to find, you guys understand, you should have to find all of these. You should have to do all of these and then add all those up, and that would be the correct answer. But what this is telling you is there is a faster way when it's at least 1. Now, if it was at least 2, it's harder, but like at least 1, that's why there's a special formula for it, okay? So they say at least 1, and we get 7/8, okay? Okay, so let's look at this. You purchase 10 lottery tickets for which the prize probability of winning some type of prize on a single ticket is 1 in 10. What is the probability that you will have at least one winning ticket among the 10 tickets? So that means that there's a chance on this lottery of 1 out of 10. So the probability of winning equals 1 out of 10, okay? So now they want to know what's the probability that you have at least one winning ticket. Now you understand if there's 10 tickets, right? How many different possible ways could I write this to have at least one of them winning? Well, I could have a win, 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 no win, no win, no win. And you guys understand, I could do this like hundreds of times. There's all these different scenarios that I would have to come up with and then add them. Or I can use the formula above, which says probability of at least one winning ticket. So what we're going to do is we're going to do the 1 minus, and now we're going to subtract the probability of no winning tickets. So what's the probability of no winning tickets? Well, if a winning ticket is 1 out of 10, what's a losing ticket? Wouldn't it be 9 out of 10? And then how many of those are there? How many losing tickets would we have to get in order to get no winning tickets? Well, that would be 10, right? 10 out of 10, all losing tickets. Now, another way you can do it on your calculator, you can just do 1. Now, 9 over 10 is just 0.9, so you can do 0.9 to the 10th. And let's do 1 minus 0.9 to the 10th on our calculator. And I get 0.65, let's say 13. Let's estimate 0.6513. I use 3 decimal places. Okay. And that's it. That's all there is to it. Okay. So it's really not that bad, but when it comes to this idea, it's not that the math is hard, it's that you got to recognize it when you see it. When they start using at least 1, that's when you start worrying, oh boy, I'm going to have to do this whole thing. So go back and make sure you write down this formula in your notes. This is definitely something you'll need for some of these more tricky problems. And if you guys have any questions, feel free to come to office hours or see me in the meeting times. Okay. All right, you guys, that'll do it for this video. Thanks for watching.